Hello, my name is Khalil Stell. I'm the founder of libhal and the libhal ecosystem, and I want to tell you about what exactly is libhal. In short, libhal is a portable, flexible, easily accessible, and reasonably easy to use hardware abstraction layer written in C++. Now, what types of problems does libhal solve? So here's something that'll happen with almost every single developer in firmware. Eventually you're going to build up some project. Let's say it's a quadruped dog, and you're going to use some controller. Let's say it's the Arduino Uno, or Nano in this case. You make it work, you're able to drive it around, you're able to have it walk forward, back and forth, do whatever. It works really nicely, fantastic. But eventually you think, oh, let me expand what I want to do with this device. Let's maybe consider adding a little display, maybe Bluetooth and Wi-Fi, maybe a camera. Maybe there's like some smart servo that you want to use, and the Arduino Uno or Nano doesn't support the interface that you need. And let's say that you've started to notice some bottlenecks. The chip just doesn't perform fast enough to do all the calculations that you need. And if you try to add in the rest of everything else here, it might not still be fast enough. Not only that, but trying to add in all these different things might just blow out the amount of RAM that you have. May not have enough flash memory to do all of this. And like we said before, the algorithms might need more speed in order to operate appropriately. So you consider the ESP32. It's got enough RAM, flash, and speed to do everything you need. You've seen people use it for cameras and displays. You've heard that it supports Wi-Fi and Bluetooth. And it just so happens to work well with whatever smart server you're going to be using. Fantastic. And one of the things that you'll notice is that your code may build and work perfectly fine for the Arduino Nano, but it doesn't really work for the ESP32. And here's like one quick example. If you look at the example code for how to use SPI, one of the communication protocols that exists in the embedded space, you don't have to know about the specifics, but when you consider SPI for the Arduino Nano, we can see it has this SPI.begin. Whereas for the ESP32, we have this object created globally. We dynamically allocate an SPI class that we call begin on it. This is the example code that they provided. As you can tell, they're different from each other. The way they're initialized is different. And these are both still Arduino libraries as defined by both companies, Arduino and the people who make the ESPs. If we try to compile with this, it would not work because it's expecting this. Now, the thing that will happen is that, well, you can actually make this technically work. You could write in your own little abstraction called global SPI. If it's Arduino, it'll return back that global SPI, and if it's ESP, it'll return back one of these SPI objects. And this is actually a typo. There shouldn't be a little asterisk there. It should just return by reference. But you get the idea. These currently, as they stand, could not be compiled into each other if you're using things that may not be exactly identical between them. There's no requirement for anything to be identical in Arduino. But this gets a little bit even worse when you actually consider not just the microcontrollers you might want to write code for, but any libraries you might be using. For example, let's say you had an application where you use the NRF24LO01. These are wireless communication devices that use 2.4 gigahertz frequency communication. It is not Wi-Fi though, and it's not Bluetooth. It's its own version of its own communication protocol. This particular library works for the Arduino Uno, Raspberry Pi, but not for the ESP32. Why is that? If you take a little look at the code, this is for selecting the chip, as it's called, and we can see here that there's things called macro definitions. So we're doing, if this particular value is defined, we're going to emit this code into the source code. If it's not, and let's say we are Arduino, then we'll emit this code. And then there's more checks and kind of compile time stuff. The problem here is that we had to write the code to support the RF24 Tiny as well as the Arduino in the same block of code. We can't really just write the driver for a generic set of hardware and then just go from there. If we want to support RF Tiny and Arduino, we need to write it for each one of those. So what this kind of does with Arduino and other libraries as well is that it results in this many-to-many relationship where if you write a driver for the RF24 and you want to support all of these microcontrollers, you'll need to write sections of the code for the Nano, for the ESP, for the Raspberry Pi, and for the STM. You need to learn how all their APIs work to make your driver work successfully. And this goes for more than just that one driver. If you're trying to make an SD card driver that works for all 4 microcontrollers, you will need to look into how their APIs are for each one of these and write your code to support each and every one of these. Same thing goes for if you make some drone software. Same thing if you're trying to control a servo. All these things, you'll need to write a driver to support each one of these. Sometimes you get lucky and the code is about the same, but in general you won't. You might think, okay, well I don't want to use the Arduino. I can just use the libraries for each and every one of the different chips. Well, you can do that, but now you've put yourself into an even worse position where now you have to develop your software for each one of the software development kits. And if Arduino was not consistent, these particular libraries are vastly different from each other, which will require even more research in order to make sure that your libraries work well for all of them. So how do we solve these problems? Well, we solve these problems with a hardware abstraction layer library. So there are a couple of them out there, and I'm going to go over a few of them. For Rust, and if you are a Rustation and you like Rust, you should use embedded HAL. If you're into Zig, there is micro-Zig. If you're into C and you like to do your drivers just in C, there's libdriver, or you can just work in Linux. And then finally, we have libhal, which is developed for C++. So why should you consider libhal, and why did I write this targeting C++? Well, let's go back to the basis of how libhal was built for. First off, let's go over the easiest thing, which is ease to use. I'm going to tell you this right now. At the moment, 2024, it is not very easy to use. We still have so much more to do, but we are planning and working towards a future where libhal is very easy to use. And I mean that mostly that we don't have enough documentation. So right now, the installation process is relatively fast. I spent a lot of time working on ensuring that the development or installation process should be around 5 minutes, assuming you have decent internet. You have to download and install the compiler. That might take a little bit, but if you have decent internet, it should only take you around 5 minutes to fully install everything and be ready to start building applications. And less than that if you're relatively fast at reading and copying commands. I want to have a searchable, I want to make sure that the drivers and APIs are easily searchable. We do have something currently, but we're still migrating it to the new setup. A lot of things are still moving in libhal, so we're working on that. I want to have tutorials on the fundamentals and how to just do basic things in libhal so that people can follow along and understand how to do things. I want to have developer guides that help developers who are using libhal build their applications for certain use cases. Explain to them when they would want to use an RTOS and when they should just use a super loop. I want to explain to them when it might be a good reason for them to move from one particular type of set of controllers to a different one. I also believe that it's really important to have easily accessible plug-and-play development devices. It makes it easy for someone to kind of just get started, get the device, and start doing all the things with them. I used to believe that you wouldn't need that for libhal because it'd be so flexible, but no matter what, people really just want to have that tried and true device that is well supported that they can just throw their stuff on and start testing. And then finally, contributor guides. So for those who want to help expand the ecosystem, there's something for them to learn about how everything's supposed to be built. For accessibility, we use Conan. When I say accessibility, I mean how is it that we get drivers to the developers that need them? And one of the issues in embedded systems in general, actually C++ in general, but embedded systems as well, is that most of the time you either have to talk to the vendor to get their drivers, or the drivers are in some repo or some location. You got to figure out a way to jam it into your build system and all of that. Conan 2 supports and makes all that much easier. It itself, because it's C++, is a bit complicated, but it provides us the ability to very easily deploy our libraries and our packages to our clients very quickly. We are sponsored by the JFrog Artifactory. They gave us a server to allow us to host all of our open source libraries. And with this, along with GitHub Actions and GitHub, we're able to very rapidly deploy out new iterations of our software quite quickly. Using any of the latest features and libraries from libhal should be as simple as changing your requirements list and going from there. Next up, and one of the key aspects of libhal is portability. You see, I believe that you should be able to take your software, take your firmware, and just change something in the command line, and so long as you set up things appropriately, you should be able to build for the Raspberry Pi, for the STM32, or for a RISC-V device. And keep in mind that we might be bare metal on an ARM Cortex-M4 device, might be bare metal on a RISC-V device, or might be using Linux with an ARM 8-class processor. It should not matter. It should be able to work. So long as, it should be able to work. It should be able to build for all of those. Now, the way that we provide that form of portability is through C++ interfaces, specifically pure virtual interfaces. Now, I don't want to speak on too much on the software side. This intro is trying to stay away from the software aspect as much, or the inner details, because I want to focus on the higher level. Specifically, let's kind of consider a simple example, tap to pay. Most people, I think, at this point have seen a tap to pay terminal. And when you see this particular icon, you know exactly what to do. You get out your card or your tap to pay enabled device, and you hover over that symbol, and then you hear for the chime to go off, you have the LEDs turn on, you know that you've been successful. Fantastic. Did it matter what manufacturer that came from? Did it matter if it came from Square, PAX, or Ingenico? Not really. But you might have noticed, depending on which one you use, some are maybe a little faster than the others. Maybe some of them are easier to work with for swiping, or sorry, not swiping, but the tap to pay seems to, be a little more finicky in some than the others. But here's the thing. You don't really care. The interface is standard. Therefore, when you see that icon, you know what you have to do. There's no more that you have to think about. You don't have to care about the fact that literally the chips and the entire design between the three competing options are dramatically different from each other. It does not matter. They're all the same. And that's how we do portability in libhal. We write interfaces that are effectively the same no matter what the implementation is. Going back to the SD card, if you use SPI, the way the SPI works is effectively the same for all devices. Therefore, the behavior you should expect from it should be the same. And hey, I don't think anyone really cares too much about the differences between these, and I think software won't care as much either. But you may see a difference. Maybe you find out that one of these peripherals, one of these implementations is faster and you need that speed. And maybe you don't need that speed, so you can then choose a device that fits the requirements that you have. And now let's consider this diagram again, this many-to-many relationship between microcontrollers and drivers. The final and most important aspect of libhal is flexibility. And this is what breaks down that coupling between drivers and their MCUs. You see, by having this common ground, this common interface between different hardware aspects or different hardware things, we can decouple the drivers needing to even be concerned about where their implementations are coming from, what microcontroller they're running on. The software and source code should not need to care about such a thing. The SD card, I'm going to use it again, requires SPI. Every one of these devices can supply SPI. The SD card just needs to fulfill the required operations over SPI in order to receive data from the SD card or to write data and store data into the SD card. Which microcontroller it comes from is not important so long as you've given it the tools it needs to communicate with SD cards. And that's what libhal does. It breaks the coupling between the drivers and the microcontroller, allowing you to write your driver once and it work for every single microcontroller in the ecosystem the moment that driver is available in the ecosystem. If the ESP32 did not have an SPI driver in the libhal ecosystem yesterday, but someone added it tomorrow, you now have SD card as an available option for any program or application that uses this library. allows you to scale your driver development far beyond what we currently get with a lot of the options that are out there on the market currently. And finally, we have to discuss why C++. Why not use a different language for building up libhal? Especially when you have to consider things like Rust, Zig, and C. Why not choose one of them? And there's a couple reasons for this. I'll tell you the most realist reason, which is C++ is my favorite language. It is the language that I find the most useful and the best tool for me to build the tools and applications that I want to build. I find that I'm faster with it. I find that I'm able to do a lot of great things with it. I have a lot of control with it. I love C++. And I'm committed to it by being a ISO C++ committee member, by helping to improve the language itself. And remember, it's volunteer work, so it's not like, I am biased because I love the language, but being a committee member is my contribution to the language itself. I also considered all the people who also really enjoy C++, contrary to public belief or popular belief. And what I found is that I bet a lot of these people would really enjoy having a tool like this. Maybe not all of them will. Maybe they will build their own version of it. But I think having this tool is something that's really important. And I would love to provide this tool to my favorite language and to my favorite community. There's also other real reasons why you'd use C++. One is maturity. It's been around for a very long time. A lot of people understand a lot of the foot guns already with C++. I think the newer languages, people are starting to realize some of the things that make it difficult to write code in those languages. We've already kind of figured out a lot of that stuff for C++. And there's a large community of people that come with that maturity. Also, it's stable. It's kind of one of the godsends of C++. The reason why it continues to be used to this day. It's changed a lot, but also hasn't changed that much. It's also well supported. There aren't that many architectures that don't support C++. C gets supported almost pretty much everywhere. But C++ is kind of second next, right after C, in my opinion. Also, the user base is massive. No disrespect. Zig and Rust are growing, and that's amazing. I think it's great that they're doing so. But C++ has been around for the last 30 years or so. More than that, actually. But it's been around for a very long time, and thus it has a very large user base and a lot of very skilled individuals. I wanted to supply a tool for those individuals. And also those who are new, who find interest in C++. Also, I think that there's so many really interesting and awesome new features coming up that I think are going to really change the game for C++. And finally, the one thing that C++ has on all of the other languages is exception handling. And to be frank, I strongly believe that exception handling is one of the key benefits that C++ has that allow it to exceed the other languages in performance and in code size. Not kidding. I actually did a talk at CVPCon this year for 2024 on how to use C++ exceptions for smaller firmware. I go into detail about my journey into discovering that Itanium table-based exceptions end up resulting in smaller binary sizes than if you were to do errors as values, as you would see from Zig, Rust, and C, or in C's case, out parameters as error handling. If you want to learn more, you can watch that talk. If you go to cvpcon.org, you can find the talk on the front page. You may have to scroll a little bit. And if it's not there, you can check on the CVPCon YouTube channel. It will be there. So when it comes to exception handling, currently, it actually reduces binary size. It reduces the overhead of calling fallible functions. It also allows for a really clear-cut separation between normal code and error code. And I have found with many of the people that I've worked with, having a good abstraction for the normal code and the error code, having that separation makes it easier for developers to read their code. But there are a lot of issues with C++ exception handling. Primarily the fact that it's slow, it's not very deterministic, and who knows what functions throw what. But that's the thing, is that that's what it is currently. That's not the future. So I've spent a lot of time working on improving the runtime for C++ exceptions And I've been able to get it to around about 88% faster than what GCC can currently do. On top of this too, as I've spent enough time looking at the binary and kind of evaluating exception handling in general, I found that because of how distinctly different exception handling is compared to normal return code, you can see its signature throughout the code base. You can see where all the throws are and what's getting thrown baked directly into the binary. This is important because what it allows you to do is it allows you to effectively build a tool where you can pass in a binary, no source code required, maybe a call graph if you have one, but you pass in your binary into this tool, and it can do a conformance test. It can say, hey, did you miss any exceptions? Or hey, are any of the exceptions going to reach no except functions? Or hey, where exactly was this exception error handled? So you can see it at a global scale, not just like from the software locally where code is being handled. You can see it overarching throughout your code, what errors are propagated and where do they land. That is something that we're working towards and building towards with libhal, because I believe that it's required in order to make code safer. But on top of this, not only can you have a tool that allows you to view and inspect and get insight into the errors being propagated out of your code, the other cool thing about exception handling is that it's swappable. Whenever you call throw, how throw is implemented is up to the implementation. Meaning that if you need speed but don't really care about code size, I can provide you an implementation that's faster but uses up extra code, or uses up extra space. Let's say you require small size, but speed's not that important. I can provide you an implementation that tries to reuse as many parts as possible in order to keep the binary size as small as possible. Need a middle ground? Sure, we might be able to provide you a middle ground. Need some special features like a stack trace? Sure. Because we're already having to unwind the frames anyway, we can just tack on where we were as we go up the frame, we go up the stack. Then we give you an API called get stack trace from exception. It'll pop out the exception or the stack trace for you. And then finally, as we've continued to do more research into binary metadata, we realize that there's like extra bits that don't need to be there. And the exception or the Itanium ABI is actually infinitely expandable. It's got some things that aren't changeable, but it's infinitely expandable from the point where it can be expanded. This is really cool because it means that we could take old binaries, old object files, maybe not do this on the action files, but like, take after you linked your old binaries, we could go through, scan the code, scan the binaries, and change the exception data to minimize it. We can remove out unneeded, unnecessary data. And we could even change the data, not only to be smaller, but to even be faster in terms of evaluation. And we could forward upgrade old binaries into the future while you can continue using them as they worked before. The only thing that would change is their exception metadata. The original code, the original assembly would stay as it was before. At least until we decide we want to build something that changes that too. So those are some of the awesome things we can get from exception handling. And actually, before we go any further, I need to roll it back just for a sec. I will say though, that I think that exception handling has been slept on in the world in terms of the way that we think about software for far too long. And there's so much performance that we're leaving on the table with exception handling that we're going to claw back with libhal as the demonstration of its capabilities. There's also some exciting new features that are coming. For example, there's reflection. This will allow us to inspect the code and write code based off of the code that is there. That's going to be such a game changer for C++. Next up, we have contracts, which I'm really excited to hopefully see into the standard. This will allow us to mark down as part of our API declarations the pre and post conditions of our APIs. And this allows us to do a variety of safety checks and a lot of correctness checks for our code. Long story to talk more about that, but that's one of the things I'm really excited about. I'm also really excited about the prospect of safety profiles. I think that they're the better alternative to some of the other options out there, such as borrow checking and using a garbage collector. I believe that we could write these profiles that basically only allow a certain subset of operations in your code. And then you could be certain that certain operations never happened in your code, and you can derive safety from that. I'm also super excited about the potential of having a standardized units library. The person who works on this, I talk to him almost every single time I go to a conference. He's a great guy, really intelligent. I love his work on units library, and I'm really excited to see that in the standard. It could also help to prevent unit type errors in your code. And then finally, we have CVP front and CVP 2. Whatever we can't really solve with the language itself, I believe that having a higher level language could allow for these types of changes. One of the biggest concerns people have with C++ is safety. And I think that we have 3, 4, and technically even 5, reflection can technically be used for safety, for improving safety. We have 4 to technically 5 different tools for improving safety in C++. And I think that it could work and still be backwards compatible with most things. So for the most part, I am quite bullish on C++ into the future. And that is it. That is your what is libhal. I hope that you enjoyed that and I hope you learned some things about libhal, about the struggles of firmware development, and how this tool can potentially be useful to you in the future. Thank you very much, and I'll see you later.